In a recent video, I described how electromagnets work, with a focus on the length contraction predicted by special relativity. That topic is one of my very favorites because it demonstrates relativistic length contraction with velocities under a centimeter per second. But many of you asked for an explanation not of electromagnets, but permanent ones. And that's a very interesting question. Let's dig into it. The question of how permanent magnets work is certainly interesting. Magnets most definitely seem like magic. It turns out that a lot of things have to line up just so to make a permanent magnet. The relevant phenomena involves fundamental particle physics, atomic physics, and small-scale physics, sizes in the ballpark of a fraction of a millimeter. It's all very complicated, but hopefully I can make it clear. So first, the basics. Magnets have two poles, a north and a south. You can't have one without the other. Like poles repel and opposite poles attract. And two magnets pointing in the opposite direction cancel each other out, leaving no magnet at all. Magnets are made of atoms, and therefore the origins of magnetism must come from the atoms or the constituents of atoms and how they move. The relevant bits of atoms are electrons and protons, both of which have electric charge and both of which can move. Moving charges generate magnetic fields. I made a video about that. It was a way cool video, by the way, so let's see if the moving charges of the atom play a role. Protons are about 2,000 times heavier than electrons, which means that they're harder to move, so the motion of protons is basically irrelevant. Well, what about electrons? Their motion is much greater, and if an electron orbited an atom like a planet orbits a star, that circular motion would make a magnet. But electrons don't move that way. Instead, they're found inside clouds surrounding the atomic nucleus. They move in all directions, and the net effect is that the motion of the electrons doesn't generate significant magnetic field. What about the protons and electrons themselves? Back in 1922, in what is now called the Stern-Gerlach experiment, researchers proved that each electron is a tiny magnet all by itself. A decade later, a team led by Otto Stern showed that protons are magnets too. So maybe that's what makes a magnet? It turns out that the strength of a proton magnet is about 700 times less than an electron magnet, so we can ignore the protons entirely, at least from a magnet point of view. That leaves the electron. Are electrons what cause a magnet to be a magnet? Well, yes, but it's more complicated than that. To begin with, what causes an electron to be a magnet? The short answer is, well, nobody knows. It's like other questions. Why does an electron have a wave and a particle nature? Why does it have an electric charge? Why does it have a mass it does? Why does it act like a tiny magnet? Why do people put ketchup on hot dogs? All of those are questions with no good answers. They're just facts for which we have no good explanation. I don't know, maybe Freud figured out the whole ketchup thing. But for the rest, like the strength of the magnet for a single electron, this is just the way the universe is. Figuring out why will have to wait for some future discovery. So is the intrinsic magnetic strength of electrons the cause of permanent magnets? Well, yes, but. Why but? It's because there is more to the story. Let's move to the next chapter of this story. According to the Schrödinger equation, and confirming measurements, of course, atoms have a series of recurring configurations called energy levels. Each energy level can accept a different number of electrons, 2, 6, 10, 14, etc. These energy level configurations explain why the periodic table of elements has the shape it does. Now, just why all of that is true would take several videos to explain, and we don't have time to do that here. For now, just accept that it's true. There's another restriction from quantum mechanics that is relevant here, and that's how the electrons are allowed to enter each energy level. For half of the electrons in an energy level, the magnetic electrons can be oriented in one direction. But once you've hit the halfway mark, the rest of the electrons have to be in the opposite direction. This is simply because of the laws of quantum mechanics and how particles with a spin of an electron congregate together. So, let's see the consequences of that. I'll use one of the energy levels that contain 10 electrons as an example. Remember that in order for an atom to be magnetic, the electrons in the atom have to be in the same direction. Otherwise, one electron cancels the other. If we put one electron in the energy level, the atom has the magnetic properties of one electron. If we put 2 electrons in, the atom acts like a magnet twice as strong as a single electron. 3 electrons, triple the magnetism, 4, 4, and 5, 5. But add a 6th electron, and that's past the halfway point. So that electron has to enter as a magnet oriented opposite the others. So this atom will only have the magnetic properties of 4 electrons. 7 electrons means the atom has the magnetism of 3 electrons. 8 means 2, 9 means 1, and 10 means 0. So this is a crucial point. Atoms with near empty or near full energy levels aren't good magnets. The good magnets are the ones with half of the orbital filled. Okay, that gets us to which atoms are magnetic, but the magnetism of a single atom isn't much. To have a magnet that will pick up a single paperclip, you need to have lots of magnetic atoms pointing in the same direction, and for that, you need to have lots of nearby atoms all working together. When nearby atoms assemble, in some cases they form crystals. Because of how the atoms interact, which is related to the specific crystalline structure of that element, some of them prefer to have all of the atoms oriented so their magnetic configurations are aligned. Such elements are called ferromagnetic. Ferrous is the Latin name for iron, which makes sense because traditional magnets are made of iron. Elements that prefer to have adjacent atoms in opposite configurations are called antiferromagnetic. Ferromagnetic materials are potentially magnetic, while the antiferromagnetic ones generally aren't. And this is a good place to point out why an atom's magnetism isn't the whole story. Chromium is a magnetic atom, but it's not a magnetic substance because it's antiferromagnetic at the crystal level. Okay, we've covered the electron, the atom, and the crystal. Is that it? Not quite. There is one more consideration. Iron is not usually magnetic. I mean, a cast iron frying pan generally isn't. Yet iron can become magnetic. So what's going on? The reason is that even if you have magnetic crystals and those crystals affect other crystals, the effect doesn't extend forever. In most iron, what you have are called magnetic domains. Those domains are small, ranging from about the size of a speck of flour used to make bread to about the size of a poppy seed. In these small domains, the crystalline structure forces the magnetic atoms to be all aligned. Each domain is magnetic. However, other nearby domains point in other directions, and the net effect is that when you add up the magnetism of all domains, the metal object isn't magnetic. However, if all the domains happen to be oriented in the same direction, the result is a magnet. So how can you make that happen? One way is to take a piece of iron, which we know contains many magnetic domains, and put it in a strong external magnetic field. That forces all of the domains to point in the same direction, and this turns a piece of iron into a magnet. So that's the basic idea. In order for a piece of metal to be a magnet, it needs 4 distinct things to happen. The first is that electrons have to be magnets all by themselves. The second is that the electrons need to be in atoms who have about half of their energy level filled up. That gives you magnetic atoms. The third is that the crystal structure has to be such that the atoms prefer to have little atomic magnets all aligned. That gives you small magnetic domains. And fourth, and finally, you need to have the domains aligned. If all 4 things are true, you have a magnet. It's not magic, it's science. Magnets have fascinated people for millennia. It's completely understandable why people once thought they had magical properties. I hope this video has given you some insight into the whole topic. If it did, please subscribe to the channel and share on social media, and come back and see more of our videos. It's some crazy stuff we talk about, but the more you watch, the more you'll come to realize one of the truest statements of science, which is that physics is everything.